The Nimitz-class aircraft carrier USS Abraham Lincoln displaces 104,000 tons at full load. It carries 6,000 people, 70 aircraft, and 2 nuclear reactors. And when a Category 4 storm sits between it and its mission, the Navy doesn't always go around. Every instinct tells you that's insane. Something that heavy should anchor. It doesn't, and the engineering reason why is more counterintuitive than you think. Today we break down exactly how a 100,000-ton ship survives and steers through open ocean storms. Let's establish what we're actually talking about. The Nimitz-class carrier is 1,092 feet long. That's longer than the Empire State Building is tall. Its 2 rudders, the physical surfaces that steer the ship, each weigh 50 metric tons and stand nearly 9 meters tall. The 4 bronze propellers that drive it are 7.6 meters in diameter, and each weighs 30 tons. Together, they produce 260,000 shaft horsepower, roughly the equivalent of 1,300 Formula One engines running simultaneously. That's not nothing. And yet in a serious storm, a wave can be 15 meters tall and move at 50 knots. The math of what happens when those 2 things meet is the entire story. Most people assume that a carrier in a storm does what any sensible captain would do: slow down, turn away, minimize exposure, point the stern at the waves, and ride it out. That is exactly wrong. And getting it wrong in 1944 killed 790 American sailors. December 18th, 1944. Admiral William Halsey's Task Force 38 was refueling in the Philippine Sea when Typhoon Cobra hit without adequate warning. Halsey's meteorologists had placed the storm 450 miles further away than it actually was. By the time the error was clear, the fleet was already inside it. Ships rolled more than 70 degrees. 3 destroyers, USS Spence, USS Hull, and USS Monaghan capsized and sank. 790 men were lost. 146 aircraft were destroyed or swept overboard. Admiral Nimitz called it a more crippling blow to the Third Fleet than it might be expected to suffer in anything less than a major action. The destroyers that sank had one thing in common: they were nearly empty of fuel. Low fuel meant low weight in the tanks. Low weight meant a high center of gravity. A high center of gravity meant that when the wave hit, there was nothing pulling them back upright. The real enemy was not the storm, it was physics, and the Navy had to relearn how to use physics, not fight it. Start with the obvious. A big ship is more stable than a small one. The carrier's sheer mass gives it what naval architects call inertia resistance, and it simply takes longer to respond to wave motion than a destroyer does. A wave that would capsize a frigate might give a carrier a 5-degree roll, but mass alone is not the answer. A carrier can be heavy and still capsize if the weight is in the wrong place. What actually matters is the relationship between 2 invisible points: the center of gravity and the meta-center. The center of gravity is where all the ship's weight effectively acts downward. The meta-center is the point around which the ship rotates when it rolls. As long as the meta-center sits above the center of gravity, the ship has what engineers call positive meta-centric height, a natural righting force that pulls the ship back upright as soon as it tilts. Modern carriers are designed with this margin deliberately wide. The 2 A4W nuclear reactors sit low in the hull, near the keel. Heavy fuel stores, ballast, and machinery are distributed below the waterline. Everything that can be heavy is kept low. The flight deck, the island, the aircraft, they are on top, but the geometry is engineered so the righting force always wins. But here's where it gets interesting. Metacentric height is only half the problem. The other half is the wave itself and the direction you take it. The most dangerous position for any large ship in a storm is beam on, taking waves directly from the side. This creates maximum roll. For a carrier, that means a 15-meter wave can catch the full 77-meter beam and apply its entire force to one side of the hull. The solution is not to run from the wave. It is to present the BU at a calculated angle. typically between 30 and 45 degrees off the incoming swell. This does several things simultaneously. It reduces the effective surface the wave can push against. It allows the ship to ride up and over the wave rather than be struck by it, and it uses the carrier's own forward momentum as a stabilizing force. The navigation team on the bridge is not just steering toward a destination. In heavy weather, every heading change is a physics calculation. Speed matters too fast, and the bow drives through a wave instead of over it, causing catastrophic green water on the flight deck. Too slow, and the ship loses steerage. The rudders become ineffective, and the carrier is at the mercy of the sea. The two rudders on a Nimitz-class carrier are hydraulically actuated. Each can deflect up to 35 degrees. Working together or independently, they allow differential thrust from the 4 propeller shafts to supplement steering, a technique where one shaft slows or reverses, while others maintain speed, rotating the hull without relying on the rudder alone. In zero visibility, 15-meter seas, this is the difference between controlled navigation and being pushed where the storm wants to take you. Most engineers would stop here, but there is another layer, and it is the one no one in 1944 fully understood until after 790 men were already dead. It is not the wave that kills you, it is the resonance. Every ship has a natural roll period, the time it takes to roll to one side and return to center. For large vessels, this period can range anywhere from 15 to 30 seconds, depending on load and design. The exact figures for military vessels are classified. Ocean swells in a major storm typically have periods of 10 to 20 seconds. Note the difference between ship roll period and wave period. As long as those numbers are different, the ship is fine. It rolls, it recovers, it rolls again, but the wave's timing and the ship's timing do not sync. When they do sync, when wave period matches roll period, you get parametric resonance. Each wave arrives exactly as the ship is already mid-roll, and instead of interrupting the motion, it amplifies it. Roll angle builds with every cycle. 5 degrees becomes 10 degrees, 10 degrees becomes 20 degrees. In a worst case, a ship in resonance can capsize in minutes. In modern naval engineering terms, what likely happened to the destroyers in Typhoon Cobra follows exactly this pattern. Light fuel load altered their roll period. That altered roll period brought their natural frequency dangerously close to Cobra's swell period, creating resonance. The storm did not overwhelm them with a single massive wave. It rocked them to death, one synchronized cycle at a time. Modern carriers track wave period in real time. When the numbers start converging, the navigation team changes speed or heading, not to avoid the waves, but to deliberately break the synchronization. Even a modest speed change can shift the encounter frequency enough to escape the resonance condition. This is what steering a carrier through a storm actually means. Not pointing away from danger, continuously solving a physics equation, adjusting heading, speed, ballast, and thrust, to stay on the safe side of a line that is always moving. Think of it like pushing a child on a swing. If you push at random intervals, the swing barely moves. Push at exactly the right moment, in sync with the natural period, and with almost no force, you can get the swing going dangerously high. The storm does not need to be stronger than the ship. It just needs to find the right rhythm. That is resonance. And the Navy's entire storm navigation doctrine is built around never letting the ocean find that rhythm. The stakes are not abstract. A carrier at sea during a storm is not alone. It is the center of a carrier strike group, 1 or 2 cruisers, 2 to 3 destroyers, a submarine, and a supply ship. If the carrier loses speed or maneuverability, the entire formation becomes vulnerable, and a carrier with a damaged flight deck cannot launch or recover aircraft, which means in a combat scenario, the strike group loses its primary offensive capability when it may need it most. There is also the human cost that has nothing to do with combat. Aircraft on the flight deck weigh 20 to 30 tons each. In a serious roll, an unsecured FA-18 Super Hornet becomes a 20-ton projectile. The flight deck crew's entire storm protocol includes chaining aircraft at multiple points, moving jets below deck to the hangar bay, and closing watertight doors. That protocol exists because the math of what happens to a loose aircraft in a 20-degree roll is catastrophic. And then there is the thing that killed Halsey's sailors that December. Not a single massive event, not a failure of courage or seamanship, a bad weather forecast, a miscalculated distance, and physics that nobody interrupted in time. The Navy does not steer around storms by finding calmer water. It steers through them by refusing to let physics win. A 100,000-ton carrier survives because its weight sits low, its righting force is engineered to exceed any realistic roll, and its navigation team tracks wave period the way a Formula 1 engineer tracks tire temperature, constantly and precisely, with the understanding that the number that looks fine right now can kill you in 4 minutes if it shifts. December 1944 taught the Navy what happens when you do not know that. 3 destroyers on the bottom of the Philippine Sea taught it better than any textbook could. Next time you see a carrier at sea in heavy weather, moving, not anchored, with the bow at that specific angle to the swell, you are watching a continuous physics calculation being solved by 6,000 people at once. The storm does not stop, the equation does not stop, and the ship does not stop. That is not stubbornness, that is engineering.